I want to focus my talk on the applied of science, on the more applied side of the science that we do in the university and its contribution to society. What can we do? How can we help? How can we implement the math, the physics, the science that is behind the applied? So I titled my talk From Bench to Bedside, from basic biomechanics research to practical solutions for effective patient treatment and quality of life improvement. And modern medicine is, and there are several doctors in the audience, yes, we want to live longer, but the main, I think, challenge of modern medicine is to give us high quality of life as long as we're here. When we're gone, we're gone. We don't care anymore. But as our former president of Israel, Shimon Peres, said once, I want to die healthy, which means have a healthy life, quality of life, and then close the eyes and that's it. So I'll try to talk about some of this technology, and I'll give you, as I call to my students, I always call it the folklore of science, meaning the dance, the beauty of science, the applied. My fundamental work is more in kinematics and motion description in high dimension spaces, but don't worry, I'm not going to get into the math about this. But then I apply to different kind of robotic devices for search and rescue, for medical application. Freddie mentioned the snakes. I'll talk about them. And then in the last 15 years, motion analysis, gait analysis, improvement of quality of life of people through understanding how we walk, how we locomote, apply it for knee, hip osteoarthritis problems. I'll talk about this. Scoliosis, Ronnie mentioned, Professor Kimmel mentioned yesterday about our work, about diagnostic of scoliosis in children. And in the last 5 years, but also very much involved in Olympic sport research with the Israeli Olympic Committee. And I'll mention a few anecdotes about that too. The last project I'll talk is a collaboration, is something we do in the last 10 years in my lab, is developing prosthetic hands for children all over the world and give it for free, and I'll mention it too during my talk. As for my career, I want to take you back to the first time I was introduced to surgical, to the medical field, and it was in 1996, I think, 97, working on my PhD with Moshe Shoam, Professor Shoam, on a robotic technology for spine surgery. The motivation was to develop a small robot that you can attach to the vertebra that you operate during spine surgery. And this robot would guide the surgeon to put screws inside the vertebrae where there is a need for spinal fixation in a very accurate way. The reason and the motivation was that 1 out of 10 screws are inserted and hit the spinal cord during surgery. This is world statistics. 5% leave permanent damage. Minimum number of screws you put in a spinal fixation is 6, so you can calculate very fast the chances to get with some kind of a damage. So the idea was to develop a very small robot. These are the first experiments we did in our medical hospitals in Rambam back in 1997. I think we took some of the cadavers from the medical schools and we tested our technology there. And this is how the system works. By the way, the system is operational worldwide. Already inserted hundreds of thousands of screws with 100% success rate worldwide. Like many surgical robotic technologies, there is a pre or intraoperative planning where surgeons are performing a virtual surgery on CT scan and MRI scan of the patients that they are about to operate on, and you could see virtual screws. The surgeon is putting the screws where he wants the robot to put the actual screws in the patient, and then after some kind of a procedure called registration, which means tell the virtual design or the design that we did on the computer what the robot is really with respect to the patient, the robot is guiding the surgeon to do this is the registration procedure, to do the surgery and insert the screws in a very accurate way. The result was Mazor Robotics out of the Technion, a very successful company that was bought, I think 4 years ago for 1.6 billion by Medtronic, I think. It was a very successful story. And then moved to Carnegie Mellon. Freddie mentioned it. It's in Pittsburgh, and for those who don't know what Pittsburgh is famous about Carnegie Mellon, the Robotic Institute, and for those of you who use Heinz ketchup, Heinz's factory is in Pittsburgh, actually. And I had 4 wonderful years there with my family in Carnegie Mellon in Pittsburgh, and we came right after 9/11. The reason I'm telling you a story is because this is how sometimes one's academic life evolves. We came right after 9/11, I think it was 3 to 4 months after, and 9/11 was the first time that search and rescue teams used robots to try to allocate survivors under the collapsed buildings, either to identify if there are survivors, but more important is to tell the search and rescue people whether it's safe to get to certain spaces in the buildings, because many, even here I think hundreds, died in secondary collapse of the buildings. Now the robots that they were using were big, they were police kind of, military kind of, but they were not able to maneuver in such an environment. So they approached us and asked us to build different kind of robots. So we thought about, what kind of robot can do and maneuver better. And the first take we did is something that looks like an elephant trunk on a regular robot. So we envision a regular robot moving inside the building to a certain place where it cannot maneuver anymore. This is 2001. And then have a flexible arm, an elephant trunk-like, which has sensor, the distal part of its arm, and then use it to manipulate and go inside the building and bring information from a remote location where the regular robot cannot look at. And do it in a non-linear trajectory. Then at the Technion, I disconnected them, and also in Carnegie Mellon, and made them more independent and more look like snakes. This is the first, I think, ever printed robot in the world. It was printed by Object Technology. This was an Israeli company, one of the world pioneer in 3D printing. This was in 2006 when I came back to Technion. We printed the snake and it moved, and I'll show you what it did. To make it move, by the way, you see a lot of wires and computers and motors inside. By the way, 20 degrees of freedom, 20 joints. Everything is controlled, embedded in one robot. It's not tethered, not wired. Everything is remotely controlled. Now, believe it or not, the easier part was to design it. The more complex part was to make it move. How do you make something that has 20 degrees of freedom move and make something meaningful, a meaningful motion? So I brought snakes to the lab, biological snakes, and I tried to observe them and look how they move, how they locomote. I had a gate lab in my facility, so we put reflectors and sensors on the robots, and we analyzed the motion, and we challenged those snakes, everything, of course, according to ethical committees. And we learned a lot. We learned a lot that biological snakes are much more superior to any robot that we can build until now. And then we tried that kind of hybrid approach, copying a little bit from nature, but then trying something else. And just to give you a quick computation of the search space of the options of gates that I have for each step of the snake, it's a huge number. It's because I have 20 degrees of freedom, or 20 joints. Each joint can move from minus 90 to 90, let's say an increment of 1 degree. Now look, multiply all the combinations there, it explodes. What do you do? Just to compare, the number of atoms that we see is around 10 to the power of 80. So you see what such a large search space I had. Of course, you can then eliminate a little bit of and assume some things that a joint cannot jump from minus 90 to 90 without moving through minus 89, for example. So you can do some kind of assumption, but it's still the search space is huge. So we ended up trying to do something more efficient, and we modeled our snake into the computer. We heard this morning digital twin, and I was smiling. I did this work in 2007, way in 2007 when we didn't have the phrase digital twin, but today this is a digital twin of the snake. So what we did is we created a dynamic model as accurate as we could of the snake, as we heard in the brilliant talk this morning about the heart, but this is about a snake or a snake robot. So we had a model of our snake in the computer. By the way, the auto industry is doing it now for almost every prototype that they produce. And we validated the model to the best of our ability. So we had a dynamic model of the snake. And then we used genetic algorithm to try to do motion planning. So you know, us human babies, some of you have brothers or children, notice that babies, before they learn to move, they move their arms and legs very chaotically. It turns out it's not that chaotically because they want to read something, they want to do something, but they don't know how to control their muscles. Their controller, the brain, is not programmed yet, so eventually motions or combinations of motions or combinations of command the brain sends to muscles that move the leg, the arm, to the target, survive and continue to evolve. And we try to do the same thing with our snake in the dynamic animation we had in the computer using genetic algorithm, where the difference is that here, instead of numbers, we had motor commands. So each bit here was a command sent to a certain motor. So we started to run a lot of simulation in the computer, trying to look for genome with successful motor commands that take the snake from point A to point B, the most efficient way and the fastest way. Those combinations that took the snake from A to B survived. Those that didn't were extinct. Of course, then we took two successful commands or combinations and we make them father and mother, created a child, and then you had to also introduce mutations sometimes, so you don't want to get stuck in a local minima. And at the end of the process, and you run it in computers, my students, my graduate students who did that, actually used to hack into all the computers in the computer farms that we had in the, and run those algorithms during the night. This was 2009 or 10. We didn't have yet strong computers. And motions were started to be generated in those animations. So you could see the snake. By the way, one of the most surprising motion was the rolling motion of the snake. Not slithering. And then we copied them to the real snakes or the robots, and the result were these motions. So you can see the snake here can roll, climb upstairs, and all kind of very complex motion, disconnect parts, leave some parts behind, roll. I think this is the only motion that the robotic snake is superior to the biological snake, because since God cursed the snake, he cannot roll, he just always had to slither. So these are snakes, they're used for search and rescue by the Israeli search and rescue teams, and it was then further developed. But remember, and by the way, to draw the attention of many interesting people, and I get the privilege to meet them and present to them. Turns out the snake is something that excites people from, I think, the story of Adam and Eve in the Garden of Eden. So I had the privilege to meet some of the world leaders and present them this kind of technology. But remember, I come from the surgical robotic field. So I was in a conference and I met this gentleman over there that sits behind. His name is Marco Zenati. You heard him yesterday. And it was in Pittsburgh, and we talked about his work on cardiac surgery. And he asked me what I do, and I say robotics, snakes. And he looked at that, and he explained to me the problems and the issues they have in minimally invasive surgery. And Marco talked about it a little bit yesterday, that you see so many holes here, and you ask yourself, what's so minimally invasive here? So many holes. And the issue is, and I remember you told me, we are operating with chopsticks. And I'm quoting you till today, Marco. We are operating with chopsticks because our tools are rigid. We have a stick and something flexible. And this was 2003, 4, I think. And so I have to have a direct line of sight from my entrance, from the entry port to the point of interest in the body. If I have something blocking my way, I cannot go around it. my tools are rigid. And then I told him about the snakes, and he said, let's use your snake for surgery. And I said, great idea, but you can use them maybe for elephant minimally invasive surgery, not for humans. Our snakes are big. I said, shrink them down. It's your problem. You're the engineer. So it took us about 4 to 5 months to bang our head, and this was the first prototype that we came about with a solution, how to shrink the snake and make it small enough so you can actually steer it. It's not a catheter. Intracavity space, in free space, create any shape that you want, like you see here around a Coca-Cola bottle, and drive it into the body, and then through the snake, perform a surgery. So in essence, what you do is you take the entry port as close as possible to the organ that you want to operate in a non-linear trajectory. And Marco yesterday presented the patent, and we created a company called Med Robotics. It was also mentioned yesterday. And this is how the system works. So there is a capital equipment. The surgeon stands near the screen there, and he drives the head of the snake, which is equipped with a stereo camera, in a nonlinear trajectory. And we call it follow the leader because the rest of the snake just follow the head or where the camera is. The surgeon drives in the image space, and the rest of the body of the snake just follow the head. So you can create any shape that you want. You steer between organs, reach deep into the body, and then once you're very close to the organs that you operate, through the snake, you introduce flexible tools and perform the surgery. And here are some examples. In 2014, we got the CE mark, then 15 FDA clearance. Was the first ever clearance from the FDA for a surgical robot. The word surgical and robot. This is the system. And this is a video which was released by George Washington University about 4 years ago. They used the system to do the first ever scar-free surgery, transrectal approach to remove a tumor in the abdominal area. And these are the videos. For some reason, they don't work on the big screen. Let me try again. On my screen, they do work. There you go. So you can see it, you're removing the tumor, and then even after you remove the tumor, you can suture and do everything inside the patient without opening it. So at the end of the surgery, you just drive the snake out the way you slithered it in, and there is a surgery with no scars, no surgery. So this is, by the way, the head of the snake, so it's about 11 millimeter in diameter, stereo vision, as I said, and it's operational worldwide. Now, other robots that I was involved in developing, I was doing some work on remember I started with orthopedics, a robot for knee surgery. And my motivation for that was that currently, knee replacement surgery is very popular, and the technology that is being used are these kind of implants, metal implants. Actually, you crown the part in the knee that is injured. I'll show you why. And you put something that looks like this, metal. So the company gives you all the tools that you need in order to prepare the bone for this implant, because the geometry is fixed and it's known. So you get all those jigs and you cut through those jigs, then you put the implant. But the world is developing, and now we're talking more and more about biological implant. So you can grow cartilage in labs, and then instead of metal, put back a biological tissue. Here, the geometry is not fixed. So the surgeon or the orthopedic surgeon will have to be a sculptor also, because he will have to remove and cut and adjust, like a dentist, the bone for the implant, which has arbitrary dimensions and shape. And by the way, this is how it's done in operating room. Modern carpentry, is my friend Tony DeGioia, one of the most famous surgeons in Pittsburgh, and actually in the United States, call himself. This is how orthopedic surgery is performed. So the idea was, just like with the spine, have a small robot sitting on the bone, scanning the surface of the bone that it needs to operate, the knee, taking points from the surface, creating a 3D reconstruction of the anatomy, in the coordinate space of the robot because the robot is rigidly attached. Then, removing the scanner with a burr, machining the bone, preparing it for the implant, because now I have the geometry, I have everything. Let me do it again because for some reason the video works well on the screen. My screen, I see it there, but on the big screen, okay. And so you see removing the material, and the work we're doing right now is removing the burr after you remove the bone, the SIG bone, with a printing head, and you print now collagen and scaffolding. So 3 in 1, we call it, scanning, machining, and printing, doing the whole sequence. So this is a technology which is now in advanced development in the lab. I mentioned the gate motion capture system I have by Vicon. It's a fairly large space that we have with cameras in the circumference of the room. Currently we have about 30 cameras there. And we have lots of sensors like force plates and EMG for measurements of muscle activity, EEG for brain, all kind of sensors to measure pressure, motion, etc. And after we measure everything, we can reconstruct motions of everything that we want to analyze, snakes, birds, people that walk in the lab, and then try to understand what goes wrong in order to figure out how to fix. One of the main problems is to understand what is wrong and then trying to develop something to fix. We focus on the large joints like the hip, knees, I mentioned scoliosis, lower spine, etc. We figure out when we started to work on that about 16 years ago, 15 years ago, that everything starts at the foot. I remember my grandmother told me when we had our first boy, buy him the best shoes because it's the most when they learn to walk, it's the most important thing, the foot. And grandmothers, you know, they're smart, they know everything. So I started to work on the foot and understand the interaction between the foot and the rest of the body. Aside from my grandmother, I also trusted Leonardo da Vinci, said that the human foot is a masterpiece of engineering and a work of art. So we spend a lot of time trying to understand the connection between the foot and the rest of the body because our body is a closed kinematic chain. For those of you who run, and I know that none of you run because none of you came to the run yesterday and none of you come to the run today. Lee, myself, and Ronnie were running alone. I'm a lone wolf with an E. If you are running and doing some sports, you would understand that if you hurt one side in your body, the other side starts to hurt because your body compensates. It's a closed kinematic chain. So we wanted to understand this kinematic chain, how muscles and skeleton is interacting together to create this closed kinematic chain. So we spent a lot of time trying to figure out the forces that we apply on the floor. Therefore, according to a guy named Newton, the floor applies to us. And these forces loads our joints, because if we were walking in space, no problems, but we don't. And then this is where our problem starts. By the way, we're not supposed to walk on two. This was a bug in evolution, probably. This is why we all have hurt. We hurt our back, knees, hips. But then we wanted to understand what is happening here and what is happening here at the foot, the pressure in our foot and how things here somehow work together. So we spent a lot of time understanding this. To do that, we used this special shoe by an Israeli company that we don't have any financial interest here. It was pure research. It's called Apos Therapy. These are shoes that have biomechanical elements in the sole of the shoe that you can manipulate them and put them in any position that you want. Dorsiflex, plantoflex also. So in essence, we're manipulating the way, the interaction we have with the environment, and we try to understand what it does to our body, to the muscle, to the forces that we apply on the floor, and to the forces that we feel in our foot. We call it COP, center of pressure, the pressure that we feel in our foot and the muscle activity. And we realized that when we move those elements medially, immediately the lateral muscle work harder to balance ourselves. Our body applies or obey to the mechanical laws that we study in engineering schools. It's a very complex machine. When you move those elements laterally, then you see the medial muscles work more. When you move them anterior, the posterior muscle work more to balance it, and so on and so forth. So there is a predictive model here that you can actually try to figure out. And then we did some EEG measurements, and we saw the motor cortex activity. We could see that what is happening also in our brain, and we correlated everything. Everything is, of course, documented in papers. You're welcome to come and read them. But then, as I said, this is very theoretical, but I'm an engineer, so I want to apply these. So how do I apply this understanding to help people? So we focused on knee osteoarthritis or problems in people's knee. Many of us will suffer from this kind of problem. It's the #1 cause of pain and disability and low quality of life in the developing countries. #3 major health concern. I was surprised to see this data. It's very popular. You probably know someone who has some knee or hip problems or knee or hip replacement. And the reason is, as I said, we're not supposed to walk on two. Look, most of us have varus legs, O-shaped. The forces come from the floor, from the foot, to the center of gravity, or in China it's called the qi, okay? Which means that they move, the forces are medial to the joints. Now, if you remember from Physics 1, you have a force, you have a joint, and there is a distance, there is a torque created. The torque is putting more pressure on the inner part of the knee, okay? It's an adductor moment. Put more pressure here. And if you also observe the knee, this is where the cartilage, which is the white, nice thing that we have here, is thinner than the other condyle that we have in our knee. So it's another bug in evolution. So the cartilage is like a sponge, and it's cushioning. It's actually observing the impact between bone to bone. When not having a cartilage, I think it's almost like driving your car with a flat tire. You feel every bump in the road. It's a bone-to-bone contact, and it hurts. So people who suffer from knee OA, knee osteoarthritis, this is what they have. They have a knee with two condyles, where in the 95% of the cases, and I can explain it also mechanically, this is where the cartilage is missing. So we understood this, and there is a correlation between the severity of the disease, disability, quality of life, and pain. And eventually, after 5 to 6 years in average, you reach to surgery. You tell your surgeon, remove this knee, give me a new knee. And it's a huge surgery. It's a big surgery. Now, this is one of the only surgery I think that I know that surgeons are trying to do as late as they can in one's life, because the more active you are, the more chances you're going to get to a redo. They will have to replace the replaced knee, because they last for average, don't tell them, 10 to 15 years. Okay, so we understood that all happens because of the forces that we apply on the floor. So I went back to Physics 1, and in mechanical engineering we call it Material 1, where we study forces and torques. And I said, if there is a force and there is a lever arm that creates a torque here, if I can move the force a little bit closer to the joint, I will reduce the torque, because the force will still be the same. I can tell the person go on a diet, but this is hard to do, especially in Romania with the good food. But I can move it, I can manipulate it, and move the pressure from here maybe to here, where there is no damage. And we did it with a shoe, and the concept was implemented very successfully. We had large studies, many years with patients. And we manipulated this, by the way, it's patient-specific. We manipulate those forces and remove the pressure from the sick part to the less sick part. And here is an example with a patient coming to the clinic, very swollen left knee, very classical knee OA, Calgren 3, almost 4 is surgery, 3 is just before. She's being, sorry, let me do it again. Run the, okay, let's see if the video works better now. Okay, good. She's not an actress, by the way. The moment we put her on a shoe, look what happens. We remove the pressure, we tune the shoe, we removed the pressure, we moved the pressure from the sick part to the less sick part of her knee. She's sent home to train, to walk an hour a day. Now notice that those elements are sphered. They induce slight instability, and for those of you who remember from control theorem, control system, that you induce slight perturbation, instability, they look for new control strategy. And this is what happens in our brain. Our motoric cortex looks for a new strategy, and after a month or two into training, adopts a new way of walking. Look how she walks after a month. She remembers, her brain, her body memorize the new strategy of gait. And it improves her quality of life, and many of these patients don't even have to get into surgery. Sorry for the companies, companies are doing billions of dollars with this kind of knee replacements, but this treatment is actually saving people or helping people's life. But interesting, and I'm not going to talk about this, is this meeting I had with the chief of orthopedic surgery in Rambam Medical Center, Michael Sudri, and orthopedic surgeons have all those toys in their cabinet. And I was taking this is a knee implant. This is the tibial plateau, the tibia part that you put when you replace the knee. There are two parts, one on the femur, one on the tibia. And I looked at it, and I saw this. And I'm a mechanical engineer, so I said this is where the material failed. And immediately, I remembered this is where, in literature, knee OA is reported. And you can see that immediately that it's in the same part. And I asked Michael, I said, what is this? And he said, this is an implant I removed after a year and a half from patients that the implant failed. And I asked him how common. He said it's very common. And it's most of the cases I see the failure here. And this is when it hits me. During surgery, surgeons give the patient a new implant, a Mercedes, or I don't know what's the best, an M2 in your Apple computer, the best processor, the best equipment, but the brain still run an old software. You still execute an old pathological gait after your knee is being replaced. Why should the brain change something? You did the surgery here. The brain doesn't know that. It takes him a while to adjust. So you're wearing and tearing the implant the exact same way you used to do with your biological knee. So we had a very large double-blind clinical study, multi-center study, and it was a kind of earthquake kind of thing for the orthopedic community, that you need to actually do the also training of gait to patients, educate them, change the software. Don't run Windows 3.1. You can run Windows 10 or I don't know. I don't run Windows. I use Mac. I don't go back to the dark side, but use the latest thing that you can do. And I'll give you the example, just the result of pain with the two groups that we had. One group got a shame device, which means the shoes with flat elements, no effect. They didn't know. I didn't know. The only person who knew was the therapist that gave them the shoes. The other group got the whole spiel, the whole treatment. The two groups started with a pain score which is about 5.67. By the way, everything above 2 is painful. The placebo group, the one who got the sham device, the pain dropped after a year to 3.5. Classical, this almost like in the literature. You read about in the literature, people still complain after 3-4 years. So it was still painful. The one who got the treatment to re-educate their gait, pain dropped to 0.6. And there were a lot of other measurements which were reported in the papers, but I'm not going to get into this. We did a lot of work also on hip replacement, what happens on our hips. I'm not going to get into this. Just one fact which is interesting, fascinating. This is the work we did with Charité. When we run, when we walk, actually don't run. When we run, our joints, our hip joints are, every time we hit the floor, they exert 5 times our body weight. So for someone who weighs 100 kilo, for example, it's 500 kilo, almost like running with a Harley Davidson on your shoulders. So this is the mechanism that destroys. But on the other hand, Wolff's law with double F, Julius Wolff, proved that the bone, in order to strengthen itself, needs to be exerted with a force. The bone builds itself proportional to the mechanical load that is exerted. So there is like everything in nature, there's contradictions. Okay, so what do you do with that? We understood everything. Now what we do is we roboticize the shoe. So instead of having a physiotherapist or an expert tuning the shoes, the shoe is a robot. So with a control system, you have a robotic shoe, you have the human person interacting, walking. We need a sensor to sense what the human is doing, and then have the shoe automatically adjust to the patient in a continuous manner, not every time you come to the clinic, but in a very continuous mode. So this is our shoe design with the mechanical elements. I'm not going to get into this details, but this is the very crude prototype, but it's a prototype, works in the lab. So you can see we can manipulate those elements with the bevel gears here, and you see the elements here, and of course the first subjects are students. You know, you just give them pizza, they come to the test, and we pay them. Everything, of course, has IRB as needed. And we just finished the clinical trials on patients, not on healthy patients or healthy subjects, as we said, closing the control loop. Now to do that, I showed you the shoe, but we also had to develop the sensors. So we developed our own sensor device, which is this. We put the sensors inside. The trick here is to know where to put the sensors. After 16 years of study, we know where to measure. So now we have everything to close the control, and we validated with validated technology. It's an insoles by a German company called Novell. By the way, every insole that they sell, it's about 3,000 euros. The system is 50,000 euros. The things that we develop cost about, I don't know, $10 maybe. They're not as good as the gold standard, but they're good enough. We validated it, and the results are the same. Really, almost the same. The deviation was negligible, and it's within what we call clinical significant. So the system is validated. Now we tested with the shoes, and what we did is, this is the interface that we do during the experiment. And what we did during the experiment is we took the elements from one point. This is the reference that we defined to the system. Then, during the gait, while the foot was in the swing phase, in the air, we moved the elements to the other side. So we created a very large perturbation. So the system detected this, and then it had to fix or to correct. So slowly, it actually fixed, and at the end of the control loop, you see that the gate or the center pressure was exactly as the reference, the original graph that we had before the perturbation. So the robotics shoe actually worked. Now we're about to build a better prototype and start distributing it to patients and doing more clinical studies, but now with patients, not just with healthy subjects. Another study that we did with a French collaborator, let me go back for a second. Oh, sorry. Good. In Paris, the second largest hospital, or one of the two largest hospitals in Europe for lung disease, it's in Versailles, next to Paris, associated with Paris 5, the Sorbonne. They had an issue with measurement of lung disease in patients, especially patients that suffer from all kind of I'll show you in a minute, Duchenne patient or pump patients. And they introduced to us a problem. They said the only tool we have to measure how much people breathe in and breathe out is spirometry, which is at the volume. I just get the volume. I don't know where the air goes to. So as a clinician, I have to put my hands on the chest and try to understand if there is symmetry or asymmetry between the right-hand side or the left-hand side and how people breathe. Can you develop a system that will tell us how to do that, so how to measure it. So we came up with an idea to put those sensors, reflectors from our motion capture system on the chest of the patient and create triangulation or triangles for each between 3 sensors and kind of mesh the entire chest. And then using some mathematical tools, which I'm going to go very fast just to show you that we do mathematics. We triangulate between each of these nodes, which is a reflector that we measure, and we have all the combinations, and we divided the chest to what the clinician understands. By the way, when you work with clinicians, you need to talk in clinician language. So upper thorax, lower thorax, abdominal. So the same things they use in their literature. And using Coursera theorem, we actually created the reciprocal vectors, the deformation gradient tensor, and the translational vector. Don't worry, I'm not going to get into the equations. Okay, this is classical mechanics. Okay, and what it measures actually is the deformation for each of these elements, triangles. How much they stress, strain, and deform. And at the end of the process, I get data. I also measure with Gauss theorem, I get the volume of this envelope, so I can know how much air went into the body. And I tell the person, lay down on the table, do spontaneous breathing, and we measure. So vital capacities, take as much air as you can, and then take it out. And spontaneous breathing. And the result is this. The color is proportional to the deformation of each of the elements. Okay? So the more red, the more deformed. Blue is extract and contract. Okay? So you see, this is spontaneous breathing. Most of the breathing comes from the abdominal area. And when you do vital capacity, you see everything is turning red. Now, okay, this is with healthy patients. Now let's see another example. This is a healthy subject, but this is a non-healthy subject. This is a pump patient, and you can see with the pump patient, something is kind of contradiction to what normal people are doing. When they breathe, the abdominal area is actually going inside, where the chest is going outside, or strength. There is it's a phase shift between the upper thorax and the lower. And this is usually happening because of the weakening of the diaphragm in our body. This is classical Duchenne patients. But here we have a very accurate tool to give the clinician data of how good and how bad the patient is. And this is with Duchenne patient, this is with pump patient. And this tool is now being implemented in this hospital in Paris. Okay, let me move to the other one. And of course, we give them all the mathematical and all the tools that they need to analyze, and this is in their language. Now, the last one of them, almost the last project I want to talk about, those 3D printed hands to children around the world. So just that you understand the solutions that are given today to people who don't have hands or lost their hands is either a mechanical tool like this or something very sophisticated. The sophisticated hands are somewhere in the range of tens of thousands of dollars to hundreds of thousands of dollars. Children cannot afford it, especially children that grow up very fast out of those hands. So we came up with an idea to design 3D printed hands that each hand should not cost more than $100. So we produced them in the Technion for my students, and it's available online, so you can download all the designs. We actually we designed the whole pipeline from scanning to CAD modeling. So only you need to have a printer to do that. And at the end of the process, we give those hands to children. To do that, we had to analyze how people grasp things and use all kind of sensors to operate those hands, and then validate the hands with robotic technology. So the robot was working for 24 hours, grasping an egg, moving it from one side to the other, by the way, without crashing the egg, because there are 4 sensors at the tip of those plastic printed hands. And then we start giving them all over the world, in the UK, We gave them in Brazil. By the way, the children can choose the color. This is, I understand, one of the best soccer team in Brazil. You know, in Brazil, you born and choose a soccer team, and you, until the last day of your life, you are a fan of this team. I was just in Brazil, so I was explained this issue. So this is in Brazil, and we gave in the US, we gave in Israel, of course. Look how this person is holding a paper cup without crashing it because of the force sensors we have at the hand. $100 max. Okay, now to control the hand is not simple as you think. You saw one of the one of the sensors that we're using was EMG or electromyographic, which is measuring the muscle activity, but it's very dependent on where you put the sensors and what did the patient or the user drink the day before, or ate the day before. So we came up with other kind of ideas to control. One of the work that came out of this project is a master's thesis from one of my students, is grasping or attention to grasp. There is a large psychological burden to operate those hands. And what she did is she designed an artificial or an AI system that understands whenever a person is reaching to grasp something. So using sensors to measure the motion in the upper arm, the hand knows immediately or automatically when the person is intention is to grasp something, as you're going to see in the video right now. So she has IMU sensors on her arms, and now she's reaching to grasp something, and the hand automatically closed to grasp the object. Okay? When she's talking and not moving her hand arbitrarily, the hand will not respond. Only when she's there to grasp something. This was a very good work, and now I want to ask Alex to give us a few more minutes, and we're done. 5 minutes, Freddie. Another option is students of Alex and I want Alex to talk about this. And this is Dean on the left-hand side, and Oren, who's our collaborator. I didn't put a picture of yourself and me because we are here, so they see our face.
Thank you, Alon. Thank you for rounding me up for this presentation. But actually, I would like to say that probably most of the credit goes to Dean. We have a student who is still a student but already a Dean. And he did, I think, an amazing work, and he's now continuing this project in his PhD. So basically, I think there is quite significant progress with building the actual actuation of the prosthetic arm, but the sensing part itself that controls the prosthesis is quite complicated. So today, what you can find typically are EMG-based solutions, and particularly surface EMG, which is relatively difficult to control a prosthesis. But basically, if you look at the anatomy of the human hand, which I don't know if Leonardo mentioned this or not, but this is also a piece of art and engineering. Actually, most of the actuation of the fingers is extrinsic because it requires considerable muscular weight and length. So basically, we are actually moving our fingers from the forearm. And if you put an ultrasound probe, so you can see this, something looks like a steak, but it's actually all the different muscles that extend and flex the fingers. If you look in the ultrasound, you can actually see all those muscles if you scan the forearm with an ultrasound probe. So basically, this is what we did. We wanted to control fine finger motion, ideally play the piano or type on the keyboard with the prosthetic arm. So we built a training system. I will just highlight very briefly what are the main ideas there. So as the input, we get a sequence of ultrasound frames. Our probe transmits at 20 frames per second. We encode each of the frames individually. So I'm showing the training part here. Each encoder is trained with a task to reconstruct the relative joint locations of the hand. Of course, we don't have the absolute location, but the relative locations. But then, so that was relatively imprecise. So then what we did, we wrapped this with a temporal model that is tasked with not only reconstructing the angular positions of the joints, but also recovering the dynamics, recovering the first and second order derivatives. So that, of course, recovers much more information. But then what we want to do is solve some end task, like, for example, playing the piano. So what we care about is the velocity and the pitch of on the keyboard, and not the exact location on the location of the skeleton. So this is data collection. Mock-up system for actually getting the locations of the joints and the location also of the sensor. So it's quite difficult to use this prototype ultrasound while playing, but still this is what the system we have. Okay, and this basically this gave us the ground truth for the skeleton location, and of course we also recorded the MIDI signal from the keyboard to get the ground truth for the pitches and the velocities. And at inference time, so of course we can do skeleton tracking. So when you compare this to the motion capture system, actually I don't know which is ground truth and which is the reconstruction, which looks quite accurate. Or we can do directly the end task using a different decoding head. So this is controlled by the ultrasound scan. And maybe I think this is more interesting, closing the loop with the... So still not at the level of playing Chopin's nocturnes, but we're getting there. Thank you.
Thank you, Alex. Freddie, 2 more minutes.
Okay, 2 more minutes for Alon, and then
then we go to questions. So just to wrap up about a little bit the Olympic work we do, as always we know, higher, faster, higher, and stronger, but the other 2 rings are smarter and more precise. We understand that you need to have science in order to get more medals. So we worked with the Israeli Olympic team, especially the surfers, and here we worked on the fin here, which has different elastic properties. So we optimized the fin per surfer. Of course, the fins come from a certain certified manufacturer, but they differ because they're from complex material. So we do it patient-specific. This is our silver medalist, Paralympics rower. And what we did for her, we optimized and we actually built the seat, a very dynamic seat that is allowed, by the way, by the Olympic Committee to do. And she practiced, or she used it during the last Olympic, and she got the silver medal. We also optimized the way we pedal, because there is a relationship between the pedaling, the foot, the steering wheel of the bicycle, so you can optimize it for our triathletes with all the equipment and the sensors that we have in our lab. And in the last few months, we work with our weightlifters. This dude comes to our lab and is doing weightlifting. Actually, no, it's her. She's the silver medalist in Europe. And she's doing weightlifting. And we measure everything that she does during the weightlifting. It's a very technical art to weightlift, because you need to optimize the center of gravity of the weight and the acceleration and go under without losing energy. So this is 80 kilograms, so she does it. I will show you. And she's sensorized, and we get the reconstructor of her motion very accurately, and we tell her trainer what she did good, what she did less good, where she need to optimize a little bit more. For her, every 10 or 20 gram can mean a medal and no medal. And we do it because we get all the graphs and all the calculations about what she did, and etc. All that you saw is thanks to my PhD students. Some of them are here. And remember, when I started my talk, I mentioned that everything I do is to improve the quality of life. So until recently, until I think 10 years ago, the goal was to live longer, but your quality of life is dropping down as you age. Now the goal is to die healthy and celebrate your 100th birthday like this lady. And this is, I think, the goal of everyone here in the audience who deals with medical technology and the interface between engineering and medicine. Thank you.